Hi everyone. Thanks for signing up for today's live broadcast on hybrid steady-state and time-resolved photoluminescence characterization. I'm Joanne Lowy, Marketing Manager at Horiba Scientific and moderator for today's event. Horiba Scientific is the global leader in spectroscopy systems, including those for Raman, fluorescence, cell optometry, and SPRI for applications across a broad range of scientific, R&D, and QC measurements. Applications benefiting from Horiba's optical spectroscopy systems and solutions include semiconductor characterization, photoluminescence of in-gas quantum dots, QA of diamond films, and more. This webinar will focus on a novel hybrid microscopic instrument for photoluminescence measurements that combines steady-state and time-resolved capabilities on one platform. Just a few important announcements before we begin. The slides will advance automatically. Feel free to ask questions during the webinar. You can submit questions by typing them in the Q&A box, which is on the Q&A widget at the bottom of your presentation window. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner or by hovering your mouse on the lower right-hand corner and dragging it. Now I'll introduce today's speaker. We're pleased to be joined today by Dr. Bridget O'Donnell, Application Scientist for Horiba Scientific. Dr. O'Donnell earned her PhD from the University of Pennsylvania in chemistry, where she employed IR UV pump probe spectroscopy techniques to study atmospherically relevant issues. She graduated in 2012 and took a position as an application scientist with Horiba Scientific in our optical spectroscopy division, where she works closely with our customers to design the appropriate spectroscopy solution for their application. Bridget, go ahead and get us started.
Thank you, Joanne. So today I will be discussing a new hybrid photoluminescence system capable of seamlessly carrying out both steady-state and time-resolved photoluminescence measurements. The goal of this talk is not to introduce new PL techniques, but to demonstrate the implementation of photoluminescence measurements on a novel platform. I will begin by giving an overview of photoluminescence spectroscopy and different dynamic processes that can occur in molecular systems. I will then move on to present some examples of different applications that can take advantage of PL measurements, both steady-state spectral measurements and time-resolved lifetime measurements. Next, I will discuss some photoluminescence techniques for both steady-state and time-resolved PL. Finally, I will give an overview of existing PL instrumentation and introduce Horiba's new hybrid MICOS PL platform. I will also show some results obtained on the instrument and finish with a summary of its strengths. Very simply put, photoluminescence is the process by which a molecule absorbs a photon and then re-emits another photon, typically at longer wavelength. Photoluminescence can take several forms, including fluorescence, phosphorescence, and Raman emission. The following energy diagram highlights the dynamic processes that can occur in a photoluminescence experiment. First, a photon is absorbed, promoting an electron from the ground state to an excited electronic state. The excited population may then relax to a lower electronic state through internal conversion or vibrational relaxation. The electron can then radiatively relax back to the ground state, emitting a photon in the process called fluorescence. The excited state population may also undergo intersystem crossing to a triplet state, followed by vibrational relaxation and emission of a photon in a process called phosphorescence. The time scales for fluorescence and phosphorescence are very different. Fluorescence lifetimes are faster, from the femtosecond to microsecond regime, while phosphorescence lifetimes are much slower, from milliseconds to hours. This is because the transition from the excited state to the ground state in phosphorescence is quantum mechanically forbidden due to the change in spin multiplicity between the two states, and therefore happens much more slowly. Common examples of fluorescence include biological systems and materials, including nanostructures and lanthanides. Common examples of phosphorescence include bioluminescent organisms and pigments. There are many applications where photoluminescence spectroscopy can be used to elucidate dynamics in the system under study. I've highlighted a few here, including semiconductor wafers, photovoltaics, light sources, and biological systems. In this talk, I will be highlighting the field of semiconductor materials and devices that can be created from them. Briefly, semiconductors are high-resistance materials that have conductivity less than that of metals, but much greater than that of insulators. There are many different semiconductor materials. For example, Group 4 semiconductors include silicon and germanium. Group 3-5 semiconductors include gallium arsenide and indium phosphide. And Group 2-6 semiconductors include zinc oxide and cadmium telluride. By introducing impurities into the crystal structure, the conducting properties of semiconductors can be altered controllably to fabricate various devices, including diodes, solar cells, transistors, and thyristors, to name a few. Characterization of semiconductor materials may be carried out using photoluminescence spectroscopy. In a photoluminescence experiment, a photon with energy greater than the band gap of the material is used to promote an electron from the valence band to the conduction band. Energy and momentum relaxation then occur towards the conduction band minimum energy level. The electron end hole can then recombine, emitting a photon in the process. This is the photoluminescence signal that is detected. By analyzing the steady-state PL spectrum, the band gap of the material under study can be determined. The following graph shows steady-state PL spectra from a variety of materials, ranging from the UV for zinc oxide to the near IR for indium phosphide. In addition to band gap determination, impurities and defects can be identified across a manufactured wafer by monitoring the PL intensity, peak wavelength, or peak width. While steady-state PL can provide a large amount of information, time-resolved PL provides additional complementary information on the system under study. For example, if there are two species with identical steady-state PL signatures, they may be distinguished by measuring their lifetimes. This could be the same material in different environments, for example, at the interface or in the bulk material, or different materials altogether. TRPL also provides a probe into the dynamic processes in the system. An example of a dynamic process within semiconductors that can be probed using TRPL is minority carrier lifetimes. This corresponds to the time between the initial creation and recombination of an electron hole in a semiconductor. The longer the lifetime is, the better the material. TRPL can also provide information on the surface recombination velocity, or the rate at which the minority carrier moves towards the surface to recombine. One can also use TRPL to probe recombination processes happening at the surface versus in the bulk material by varying the wavelength used for excitation, where longer wavelengths correspond to greater absorption depth. The temperature of the sample can also be varied to change the ground state of the electron hole. The lower the temperature, the closer to the valence band minimum the electron hole will lie. In the next few slides, I will discuss some examples of applications where adding lifetime to steady-state measurements helps to elucidate the processes happening in the sample under study. Typically, in photovoltaic systems, the quality of the material is assessed by electrical measurements after the device has already been fabricated. This necessarily eliminates the possibility of carrying out any on- or in-line processing during manufacturing. However, by measuring the lifetime of the material using TRPL, the material process can be changed or optimized in real time before fabrication. This is because PL lifetime is directly correlated with the open circuit voltage, an indicator of thin film photovoltaic efficiency. In the example shown here, the system under study is a cadmium sulfide, cadmium telluride photovoltaic device. In most TRPL experiments, lifetime measurements are carried out at a single PL wavelength, typically the peak wavelength. However, a spectrometer-based system was used here to map the temporal information across the entire PL emission curve. A 3D surface plot is shown, which maps out the PL signal as both a function of wavelength and time. By taking slices through this curve, one can look at either the spectral information at a particular time, or look at how the spectrum changes as a function of time. By measuring the lifetimes at different PL wavelengths, the carrier dynamics of different spatial regions of the device can be probed. In addition, in this experiment, the authors of this study varied the excitation wavelength, thereby changing the absorption depth in the sample. Shorter wavelength excitation has a shallower absorption depth and can probe the cadmium sulfide-cadmium telluride interface, while longer wavelength excitation near the band gap is absorbed deeper in the sample, reaching the bulk cadmium telluride material. Semiconductor materials are also often used in the manufacturing of light sources. Gallium nitride and its alloys are particularly attractive for the fabrication of blue-green and UV LEDs, OLEDs, and laser diodes. TRPL can be used in combination with spectral data to determine the dynamics of the carriers in such systems. In the example shown here, the system under study is gallium nitride grown by hydride vapor phase epitaxy. The top graph shown here displays the steady-state PL spectrum of the resulting sample. The transition at 3.47 electron volts was assigned to the donor-bound exciton, while the shoulder to higher energy was assigned to the free exciton, and the peak at 3.45 electron volts was assigned to the acceptor-bound exciton. The lifetimes for the donor-bound and free excitons were measured and are shown in the lower figure, where the blue curve corresponds to the donor-bound exciton and the red curve represents the free exciton. Because the free exciton lifetime matches closely with theoretical calculations, and the fact that the data could be fit to a single exponential suggests that there's a very small number of defect levels in the sample, or that their relaxation time is very long. Moving away from semiconductor materials, another application where PL measurements are advantageous is rare earth doped glasses. These species have potential applications in lasing materials, fiber optic materials, and nonlinear optics. Because the electronic transitions of rare earth ions cover such a broad wavelength range from the UV to near IR, they are attractive possibilities for lasing materials. The potential of a lasing material is related to the radiative and non-radiative properties of the material under study, which can be probed using both steady-state and time-resolved photoluminescence. In the example shown here, a steady-state PL spectrum is shown for a sample of praseodymium-doped sodium borosilicate glass. Two transitions at 490 nanometers and 672 nanometers were identified as being possible lasing transmissions based on the calculated laser parameters, namely the spontaneous emission probability, branching ratio, radiative lifetime, and stimulated emission cross-section. The transition at 672 nanometers has a particularly large value for the stimulated emission cross-section because of the drop in covalency associated with the environment surrounding the praseodymium ion. Making empirical measurements of the PL lifetimes at each of these electronic transitions would confirm that these two particular transitions are good choices for lasing. For such a study, a system that can seamlessly integrate both steady-state and time-resolved PL in a single platform would be very advantageous. To record photoluminescence spectra, there are a variety of different experimental setups that can be employed. For example, the measurement can be done using filters or a dispersive element as in a spectrometer. The measurement can either be done on the macro or microscopic level. It can also either be done in an ambient setup or temperature controlled with a cryostat. For time-resolved lifetime measurements, there are a variety of techniques including using a PMT with digital oscilloscope or boxcar integrator, the stroboscopic optical boxcar technique, and time-correlated single photon counting. In steady-state PL measurements, a CW light source is generally used with the mechanism for distinguishing the emission spectrum, whether that be with filters or spectrometer. The detector response time in this case does not need to be fast since we are only interested in the spectral information in this type of experiment. The resulting spectrum can reveal information on the energy levels of the electronic states in the system. Borrowing from the rare earth example I showed earlier, we see that the various peaks in the PL spectra correspond to 4 different electronic transitions in the energy diagram. Now, if we were to fix the wavelength of the PL emission at one or all of these points sequentially, we could also carry out time-resolved PL, which would reveal more details on the dynamics of the system. In a time-resolved PL setup, a pulse source is required, with the final system temporal resolution depending on the pulse width of the source. As in a steady-state PL experiment, the emission must be resolved using either filters or a spectrometer. The detector response time must be fast, with the transit time spread contributing to the overall temporal resolution of the system. In a TRPL experiment, the excitation pulse excites molecules from the ground state to an excited electronic state instantaneously. The population then begins to randomly decay back to the ground state, with each excited molecule emitting a single photon in the process. The lifetime is defined as the 1/e point, or the point at which 37% of the population remains in the excited state. Although there are other available methods for carrying out time-resolved photoluminescence measurements, today I will be discussing time-correlated single photon counting, since this is the technique that is used in the results presented later. TCSPC is a digital technique with well-defined Poisson statistics. In a TCSPC experiment, the source is pulsed and sends a trigger at the same time to the time digitizer to start counting, much like a stopwatch. The sample is irradiated and the molecules are promoted to an excited electronic state. As the population decays back to the ground state, photons are emitted which are collected by the detector. The first photon to hit the detector results in a stop trigger that is sent to the time digitizer to effectively stop the stopwatch. Each photon is registered as a single count and sorted into its appropriate bin based on the arrival time relative to the start pulse. Since TCSPC is based on the arrival times of photons after excitation, the results are not affected by changes in the source intensity. In other lifetime techniques, fluctuations in the source may have an effect on the result and therefore the final analysis. In addition, TCSPC offers very high sensitivity and precision with resolvable lifetimes in the picosecond range. As you can see from the instruments shown here offered by Horiba's fluorescence group, there are many different platforms for photoluminescence measurements. Historically, systems for steady-state and time-resolved photoluminescence have evolved on separate platforms. For example, this slide shows a selection of steady-state instruments with both smaller benchtop systems and larger, more complex, customizable fluorescence systems. The following instruments are designed for time-resolved fluorescence with both filter-based and spectrometer-based options, as well as a microscopy system. More recently, hybrid steady-state time-resolved systems have been assembled by adding TCSPC sources and detectors to existing steady-state systems. These instruments have been used for a wide variety of materials and applications. The new instrumentation presented here is geared more towards materials, specifically solid, wafer-based semiconductor samples. Within this sphere of applications, there are various manifestations, including macro or microscopic, ambient or cryogenic, single point or mapping of surfaces, and wavelength ranges that can vary from the UV to near IR. The new MICOS system combines steady-state and time-resolved measurements on a single, compact, and complete instrument. The system is highly customizable and flexible, with the ability to accommodate multiple laser sources, including those for steady-state and time-resolved PL measurements. The wide array of choices for spectrometers and detectors means the system can acquire spectra across a wide wavelength range from the UV to near IR. The system also benefits from the direct coupling design, which leads to higher throughput. Finally, the microscope head's flexibility means that many different sample handling options can be accommodated. The following schematic shows the general layout of the MICOS system used in the results to follow. Two sources are employed, a CW laser for steady-state PL and a pulse source for TRPL. The sources are coupled via fiber to the microscope head, which is directly coupled to the spectrometer. Two detectors are mounted at the exit, a CCD for steady-state measurements and a picosecond photodiode for TRPL measurements. A delta hub timing module accepts a start pulse from the delta diode source and stop pulse from the PPD detector. All hardware was controlled through a PC and software for both steady-state and time-resolved PL, were used to analyze the results. For the light sources, a CW laser was used for steady-state PL single-point and mapping measurements. A pulse delta diode laser source was used for single-point, time-resolved photoluminescence measurements. The delta diode source has a maximum repetition rate of 100 MHz and pulse width of less than 100 picoseconds. A wide variety of delta diode sources are available, ranging from the UV to near IR. A bifurcated fiber was used to couple both sources to the microscope head, eliminating the need to physically swap sources when changing experiments. The output from the bifurcated fiber is collimated and sent into the microscope head, where it reflects off of a dichroic and is directed through a microscope objective to the sample under test. The resulting PL signal is collected back through the microscope objective, passes through the dichroic, then passes through another laser blocking filter before entering the spectrometer. This direct coupled design provides much better throughput than traditional microscope systems, which are often fiber coupled to spectrometers, resulting in greater losses. In addition, the microscope head includes a white light illumination source and vision camera for aligning and viewing the sample and laser spots. For maximum flexibility, the microscope head can be configured in either a down or side-looking configuration. It can easily accommodate mapping stages with either manual or automated control in all three axes. As shown here, the microscope head can accommodate ambient stages as well as various cryostats. One example shown here shows a cryostat custom mounted to an XY stage, and another example shows an upright cryostat used with a side-looking MICOS. The high degree of modularity and customizability makes measurement of virtually any sample possible. While all the systems shown so far have been equipped with an IHR 320, there are multiple spectrometer options. The 320 mm focal length spectrometer gives a resolution of 0.06 nanometers, while the 550 mm focal length spectrometer gives a higher spectral resolution of 0.025 nanometers. Both spectrometers use a triple grating turret design, which allows for 3 gratings to be mounted at once with automated switching between them. Coupled with Giovanni Vaughn's large grating catalog, the spectral range over which the spectrometers work extends well into the infrared. Finally, the spectrometer is equipped with 2 exit ports so that multiple detectors can be mounted without the need to swap between them when switching from one experiment to another. In this set of experiments, a CCD was used to record steady-state PL single-point and mapped spectra across the surface. Because the CCD is able to record the entire spectrum in a single shot, fast acquisition speeds can be attained, which is especially important when recording mapping data. Although not used in the results presented here, the Synapse indium gallium arsenide linear array is also a good choice for steady-state PL in the near IR with response out to 2 micron. For time-resolved PL, a picosecond photodiode was used. The detector has spectral sensitivity up to 920 nanometers with a transit time spread of 180 picoseconds. There are many other detection options available that extend further into the infrared, including near-IR PMTs with response out to 1700 nanometers. While there are several options for TC-SPC electronics, the Delta Hub timing module was used in this case. The Delta Hub has an ultra-short 10 nanosecond dead time and is fully compatible with a Delta diode source and PPD detector. The minimum lifetime measurable with the Delta Hub is 25 picoseconds. Although not used in this set of experiments, the FluoroHub A+ is another option which has the best ultimate timing resolution at 400 femtoseconds per point. This extends the shortest possible lifetime measurement down to 5 picoseconds when used with an MCP PMT. Finally, 2 different software packages were used, LabSpec for steady-state PL and DataStation for time-resolved PL. LabSpec integrates all hardware control, including the spectrometer, CCD detector, mapping stage, and vision camera. It includes a large array of tools for processing and analysis, including analysis of mapped PL spectra, for example, peak wavelength, peak intensity, peak width, and area. DataStation integrates control of the TC-SPC components, including the Delta diode source, Delta hub timing module, and PPD detector. The data analysis software package includes many tools for analysis of lifetimes, including multi, batch, and global exponential fitting, as well as energy transfer models. Now that I've gone through all of the individual components of the system, let's take a look at some examples of different samples that have been run on the system. The first set of results I'm going to review were recorded on a 2-inch by 2-inch indium phosphide semiconductor wafer. The set of data you see on the left-hand side of the screen corresponds to steady-state PL mapping spectra over the entire surface. In this case, I have shown 3 graphs plotting different PL parameters. The top graph shows a map of the PL intensity, the middle graph shows a plot of peak PL wavelength, and the bottom graph shows a plot of the peak width. As you can see from the differences between the 3 sets of data, different information can be gleaned from analysis of different PL parameters. In addition, changes in band gap or identification of defects or impurities can also be carried out. On the right-hand side of the screen are representative lifetime data that could be recorded from different points on the wafer. With the PL information obtained from the steady-state spectrum, single points on the sample can be identified and lifetime measurements can be carried out. Since both measurements can be made on the same platform, this ensures that the 2 measurements are made on the same spot within the sample. By measuring the lifetime in semiconductor samples, the user can probe the dynamic processes in the sample under test and assess the quality of the material. In addition to spatially identifying areas on the sample, the use of a spectrometer in this system also allows for lifetime measurements to be made at different wavelengths in the PL spectrum. In a filter-based system, the user would be restricted to a set of wavelengths and bandpass dictated by available filters. The new MICOS hybrid PL system provides much greater flexibility with virtually limitless choices for detection. The second set of results were recorded with a sample of praseodymium-doped borosilicate glass. In this case, the steady-state spectrum is shown in the top graph, and the lifetime recorded at a single point is shown in the bottom graph. From the introductory slides where I discussed another example of a rare earth-doped sample, you'll remember that there were several electronic transitions as indicated by the resulting photoluminescence spectrum. Although I have not assigned electronic states in this sample, you can see from the steady-state spectrum that it appears as though there are multiple electronic transitions as indicated by the multiple PL peaks. To measure the lifetime, I fixed the wavelength on the peak around 650 nanometers and used TC-SPC to build up a histogram of the PL signal over time. I then analyzed the results using data analysis software and was able to fit the lifetime using 3 exponentials. By measuring the lifetimes at different points in the PL spectrum, the dynamic processes within the molecular system can be probed for different electronic transitions. As in the example presented earlier, the lifetime provides a probe into the environment in which the rare earth ion is held. The MICOS hybrid system provides a platform which is able to carry out lifetime measurements along different points in the sample and at different PL wavelengths. In conclusion, the new MICOS PL system seamlessly integrates both steady-state and time-resolved photoluminescence on a single platform. The design allows for a high degree of flexibility and customizability to fit almost any sample's requirements. Specifically, this system shows promising results for semiconductor wafers, where steady-state PL can be used to map and analyze the PL signal over an entire surface before carrying out single-point lifetime measurements. The fact that both measurements can be made on the same platform means that the user can retain co-location of the sample in both measurements without the need to switch instruments. The wide array of hardware options for the spectrometer and multiple detectors provides the possibility of detection from the UV to near IR, while direct coupling of the PL signal to the spectrometer results in very high throughput. The system can be used to characterize semiconductor materials and their corresponding devices, such as solar cells or light sources, in addition to rare earth-doped glasses. Thank you for your time and attention, and I would be happy to take any questions you might have at this time.
Thanks, Bridget. Before we get started on the Q&A, just a reminder that you can submit questions by typing them in the Q&A box, which you can find at the bottom at the Q&A widget at the bottom of the presentation window. Our first question what is the laser spot size on the sample?
So the spot size on the sample depends on the objective that's being used and whether the light source is fiber coupled or direct coupled. The limit of what can be resolved is a 1 micron spot size with a 100x objective, and that's with a 532 laser, and direct coupled as opposed to fiber coupled.
Can lifetime measurements be automated for different spatial locations?
Yes, yes, they can. So you can effectively do a lifetime map where you define points along a surface and then ask it to calculate the lifetimes or measure the lifetimes at each point.
Okay. Can parts of the system be purchased individually? For example, I already have an IHR 320.
Yes, of course. So as part of OSD, we are a components group, so this is kind of standard what we do. You can, if you already have an IHR 320, you could add the MICOS microscope head plus a source and a detector to be able to do time-resolved PL.
How big is the excitation spot in regards to spatial resolution?
Right, so this is the question. So it's 1 micron, but it depends on the objective size and the type of coupling.
Okay. And how long does it take to map a 2-inch by 2-inch wafer?
So it takes about 2.5 minutes to cover the whole size, and we're able to take advantage of Swift mode and lab spec to be able to map fairly large areas relatively quickly.
Excitation wavelengths, you didn't answer that yet, right? How many excitation wavelengths can you accommodate?
So that's an interesting question because in theory, we can accommodate many different wavelengths. So the whole idea of this system is that it's very modular. So we've done systems with up to 4 different wavelengths of excitation, but there's no reason that we couldn't implement additional wavelengths.
Okay. Is TC-SPC generally more used for TRPL compared to using a PMT with a digital oscilloscope? If so, why?
We didn't have it. Oh, the sound. Yes. So TC-SPC has the advantage of being able to measure shorter lifetimes then can be measured with a PMT with a digital oscilloscope. So it's attractive for that reason.
Is there a standard method for determining DC offsets in analog signals from a PMT photodiode in TRPL?
Okay, so the advantage in TC-SPC is that it's high sensitivity and background free, since you're just detecting photons as they come, as they hit the detector one at a time.
Okay. Can you use EMCCDs as detectors for ultrafast and weak measurements?
Yes, so in my example, I used a regular CCD, but certainly if you used an EM CCD that has faster available ADC rates and also has the advantage of being able to use fast kinetics mode like crop or burst mode, you can definitely carry out your experiment faster that way.
Okay, and can you tell a bit about the sample handling implemented in MICOS? Is it a microscopic stage or cuvette or solid sample holder of some sort?
It is a custom microscope head, so it's not like a typical traditional microscope. We have control over all the optics in the system, which makes it more flexible than a packaged microscope would be from a microscope manufacturer.
Oh. Yeah, I don't know if they heard it. Okay, anything else? Oh, what is the footprint of the system?
So the system fits on about a 2 foot by 4 foot area, so it's relatively compact, especially relative to some other bigger photoluminescence systems.
And what is the maximum sample size that can be accommodated?
That's a good question, actually. So it depends on the length of travel of the stage in use. But we've gone all the way up to a stage which can do 150 millimeter travel.
Okay. I think we've answered everyone's questions. If there's anything else, feel free. I have another question. Can the sample stage accommodate electrical probes for electrically biased photoluminescence?
Yes, we've done this before, actually. There's a tech note on our website that talks about exactly such a setup with the MICOS, so feel free to check there.
Okay, great. Thanks, Bridget, for your answers. If anyone submitted questions that weren't answered, we'll answer them via email, or you can reply to my thank you email and we'll follow up. Thank you, everyone, for questions and participating in today's event. I'd also like to thank Bridget for her presentation. This webcast will be available for on-demand viewing through August of next year, and you'll receive an email from On24 alerting you when this is available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event or for you to watch it again. We look forward to seeing you next time. Thank you. Bye.